A couple of weeks ago, I released a video on how electric guitars work and how their sound is electrically amplified. But today I'm going to answer how acoustic guitars work. How do they make sound? And why do any guitars, acoustic or electric, sound like a guitar? When you pluck a guitar string, it makes a sound. But why? What is sound? Well, you might think that sound is its own thing, a blob of sound stuff that travels through the air. But that's wrong! Well, kind of wrong. Instead, sound is a wave that travels through a medium, like the air or water or the ground, or really anything. Now, for the purposes of this video, I'll be talking about how sound moves through the air. Now, all sound comes from a vibration of some sort. For example, a vibrating bell, or your vibrating vocal cords, or something like a vibrating guitar string. See where this is going? So if we take something like a vibrating guitar string and zoom down to the atomic level and look at it in slow motion, we can see that as it vibrates, it pushes air molecules in front of it out of the way. Then those air molecules push the next air molecules out of the way. And then those air molecules push the next air molecules out of the way. And then those air molecules push the next air molecules out of the way. And so on. And this string keeps vibrating, so it's constantly sending out new pressure waves throughout the air. And these pressure waves are what sound is. Our ears interpret these pressure waves as sound. You can think of it kind of like a slinky. I can send pressure waves from one end to another. Now the slinky is pretty limiting because you only have a few feet to work with, but in reality the pressure wave would go that way for a really long time. But the way guitars work is much more complicated than that. That's how vibrating things make sound travel through the air. But how does a guitar sound like a guitar? If all sound is just these simple vibrations, why do things sound different? Why does a guitar sound different than a piano? Sound different than a bell? Sound different than a human voice? Well, to answer that question, we first have to learn a little more about sound. Let's start by looking at how a guitar makes sound. Right after the string is plucked, you can see two pulses traveling up and down the string. And once they hit the ends of the string, they reflect back and go the other way. But this really isn't helpful to understanding how a guitar works. I mean, sure, little pulses travel up and down the string, but how does a guitar actually make sound? Well, when you pluck a guitar string, it vibrates at its fundamental frequency. This is the note of the string. For example, this is an E, and it vibrates at 82.4 hertz, or 82.4 times per second. Now, when you pluck it, it moves in a smooth standing wave called a sine wave. But it doesn't only move in that way, it also moves like this, and 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 like this. The first one is called the fundamental frequency, the next one is called the first harmonic frequency, then the second harmonic frequency, and so on. But how can the string vibrate in multiple ways at the same time? Well, it doesn't really. It vibrates in a combination of these frequencies. You just add all the multiple waves up and you get something like this. You're just adding the height of each wave at each point to get what's called the superposition. Now, this isn't what a guitar string actually looks like when it's vibrating, by the way. This is just a random example of adding random frequencies together. Now, these different harmonics create different sounds. For example, if I play the fundamental frequency of an E note, it sounds like this. And if I play the first harmonic, it sounds like this. And the second harmonic, the third harmonic, the fourth, the fifth, the sixth, and it goes on and on. The higher the harmonic, the higher the pitch. This is because higher harmonics have to bend back and forth faster to keep their shape, and faster vibrations are associated with higher pitches. How much the string vibrates is called the amplitude. Now, a tiny vibration creates a quiet sound, a low amplitude. But a much larger vibration creates a much louder sound, a high amplitude. So each individual string vibrates as a combination of individual harmonic frequencies, but each of those harmonic frequencies vibrates at a different amplitude. And when you add all those waves up, it looks like two pulses traveling up and down the string. And even though the string vibrates as a combination of all these frequencies, the individual frequencies are still expressed. So for example, if I pluck the low E string on my guitar, I'm not only hearing the low E, the fundamental frequency, but I'm also hearing the first harmonic, the second harmonic, the third harmonic, and so on, all playing together at the same time. And when they all blend together like that, they create that rich sound that we know as a guitar. And the most prominent frequencies will be the fundamental frequency and the first few harmonics. But if you listen carefully, you might be able to hear even past the 10th harmonic. But the vibrations of the strings aren't always the same. Now, when you pull a string back with your finger or with a pick, you're pulling the string into a triangle shape, not a smooth sine wave. So what ends up happening is right before you release the string, you're exciting certain harmonics. And by exciting, I mean getting those specific harmonic frequencies into motion. Now, each harmonic has something called an antinode, or multiple antinodes. An antinode is a place of maximum movement on the string. So these are the antinodes. Now, when you pluck a string, you are creating an antinode in the place that you plucked it, because the place where you pluck it is the point of maximum movement on the string. So, for example, if you pluck a string right in the middle, you are creating an antinode right in the center of the string. And consequently, you will excite the harmonics with an antinode at the center. And interestingly enough, you'll pretty much only excite the harmonics with an antinode at the center. So these will vibrate and these won't. Now, as a result, it kind of creates a more mellow, less interesting sound. And on the other hand, plucking a string really close to the bridge or really close to the neck creates a high, twangy sound. This is because you're exciting more higher order harmonics. And the place where you pluck a string is going to be an antinode, so you must be stimulating these higher order harmonics because those are the only harmonics that have antinodes all the way down here. You can even hear, as I slowly move the pick from the bridge towards the center of the string, that it loses that high, twangy sound. And depending on what you use to pluck the guitar string can also change its sound. For example, your fingers, a pick, or a quarter, and they all sound a little different. Depending on the initial conditions of the string right before you release it, that will change how the guitar sounds. Now, a pick and a quarter are both a bit harder, so they strike the string a bit more abrasively, and in turn, they're able to create those higher order harmonics, and as a result, sound higher and more metallic. Now, there are so many subtleties here, and the tiniest things can change how the guitar sounds. But the main takeaway is that depending on how you pluck the string, that will change the combination of the fundamental and harmonic frequencies. They'll vibrate differently and at different amplitudes. And that different combination of the fundamental and harmonic frequencies sounds different to our ears. You can actually see this on something called an audio spectrum graph. Now, when I pluck the B string on a guitar, you can see it makes a spike right here at 246.94 hertz. Now, but it also makes a spike here. Now, that's the first harmonic. And it makes a spike here, that's the second harmonic, and a spike here for the third harmonic, and the fourth, and the fifth, and it goes all the way up. Each spike is a different harmonic frequency. But what if I pluck all the way up here? Well, then I'm stimulating those higher order harmonics because I'm plucking it closer to the bridge, so those higher order harmonics are more emphasized. But here's the thing, higher harmonics also die out quicker because they bend more and more frequently to keep their shape. So as a result, over time, those higher harmonics will mellow out and the lower harmonic frequencies become more prominent. A single string vibrating by itself isn't actually very loud at all. But in the case of a guitar, the strings are attached to the body of the guitar. So the vibrations of the strings carry into the rest of the guitar. So now instead of just the strings vibrating, now the entire guitar is vibrating. And that is able to push much more air back and forth. Remember how all sound comes from vibration. So this much larger surface area is pushing much more air back and forth, creating a much louder noise. You can actually feel the guitar vibrating after you strum it. The front of a guitar is actually called a soundboard because that's where most of the sound from the guitar comes off of. That's right, most of the sound comes directly off the front of the guitar, not from inside. So this raises the question, what does the sound hole actually do? Well, you might think that it amplifies the sound coming off the guitar somehow. But that is wrong. Now, the sound hole doesn't actually amplify the sound. Here, have a listen. I'll play the guitar regularly. And then I'll play it with the sound hole covered. Notice a difference? In terms of volume, it's pretty similar, but when you have the sound hole covered, it sounds a little more high-pitched and not quite as full. Here, I'll play them again. So the sound hole does help with making lower notes more audible. In addition to vibrating the air outside the guitar, the soundboard will vibrate the air inside the guitar. So this vibration will reflect off the back of the guitar and then bounce out of the sound hole. Lower frequencies are more pronounced through this method, and therefore having a sound hole creates a richer and fuller sound. And then there are the specific notes the guitar sings. Low E, A, D, G, B, and high E. And then I can move my fingers up and down the frets. And I can also play scales or bend the strings. So how can I get all these different sounds? Well, there are three main factors that affect the pitch that a string vibrates at: tension, density, and string length. Now, to start, tension. If you pull a string really tightly, it wants to vibrate faster, and our ears perceive faster vibrations as higher pitch. So these tuning pegs over here actually control the tension of the string. So if I turn the tuning peg so it's tighter, the pitch goes up. And if I turn it so it's looser, pitch goes down. You can also bend the string, so as you pull it, it makes the string tighter. And then there's the density. If the strings are really dense, they'll vibrate slowly, and the pitch will go down. But if the strings are light, they'll vibrate faster, so the pitch goes up. Now in this case, density can also mean mass per unit length. For example, the E string and the G string are both made out of the same material, so they have the same density, but the E string is much fatter and thicker, so it vibrates slower because it has more mass for the same length of string. So it vibrates slower and creates a lower sound. And lastly, there's the string length. Now, if you have a really long string, it takes a lot more work for it to vibrate back and forth. So it will vibrate slower and therefore create a lower note. But if you have a really short string, it vibrates quicker and therefore is able to produce a higher note. Now, in the case of a guitar, you can simulate changing the length of the strings by holding your finger over the different frets. Say, for example, I hold my finger here, the string is only vibrating from this point to this point instead of the whole length. So as I move my finger up the neck, you can hear the pitch go up. So when you put all this together, tension, density, and string length, you can play things like scales across different strings, or different chords, or riffs. Remember how towards the beginning of the video I asked, how does a guitar sound like a guitar? If all sound is just these simple vibrations, why do things sound different? Well, now we can answer that. The difference is from the different amounts of the fundamental and harmonic frequencies. You can use this interactive website called a Waveform Generator to change the amplitude of different harmonics and see what it sounds like. Link is in the description. So all instruments just produce a different combination of the fundamental and harmonic frequencies. So that's why the same notes played on a guitar, a piano, a flute, a bagpipe, a tuba, or a clarinet will all sound different. And this is because the way each of those instruments produce sound is different. So even though they're playing the same note, the combination of harmonic frequencies they're producing is different. So overall, it sounds different. And as you can see, they all sound different. They all have their own unique sound. Now, what's more important than just how the strings vibrate is how the body of the instrument responds to those vibrating strings. For example, in the case of a guitar, the soundboard of a guitar is about 1/8 of an inch thick. So the guitar tends to vibrate low or mid-range frequencies more easily. But in the case of a banjo, the head of a banjo is about 1/100 of an inch thick. So it's much easier for it to vibrate those higher harmonic frequencies and vibrate them for longer, which is why banjos sound so high and twangy. Now, pianos are really interesting. They work by having hammers positioned right under here that strike the strings. And grand pianos are really cool because each note has its own string. And as you can see, the really low notes all the way down here have really long, really thick strings. And the really high notes have really tiny, really thin strings. And bowed instruments are really cool because they have a continuous supply of energy from the bow, so the same note is sustained, and it takes on different characteristics. There are so many subtleties that can change the different sounds between different instruments and different guitars and even different ways of playing on the same guitar. And we often like to assign adjectives to different sounds like dull or tinny or sweet, but when it comes down to it, the only real differences between those sounds are the different combinations of frequencies. And tiny differences in the way a guitar is made can affect the sound. Different places you pluck the string, whether or not you use a sound hole, the string length, tension, and density, and the overall shape and nature of the body of the instrument all significantly affect the sound. So maybe next time you listen to or play a guitar, you won't think of it just as a frame with vibrating strings, but as an achievement of human engineering and craftsmanship, replete with complicated physics, those different combinations of harmonics, and as carefully crafted works of musical art. I'd like to thank Dr. Timothy Jenkins of the University of Oregon, who answered several of my questions on guitars over email, and I'd like to send a massive thank you to Dr. Richard Mark French, author of Engineering the Guitar, Technology of the Guitar, and professor at Purdue University, who generously took his time to speak with me on a video call answering all my questions on guitars. Thank you so much for all your help, and thank you for watching. If you haven't subscribed already, consider subscribing, and I'll see you next time. Do you want to see a magic trick? I can make a guitar appear out of thin air. Ready? Pretty cool, right?